All right, it's 11:21. Let's go ahead and get started, shall we? So welcome to the Quantum Internet Research Group QIRG meeting, proposed research group, I guess I should have in the title still. I'm Rod Van Meter. I'm chairing the session this morning. And we have a Jabber scribe, maybe. We need a note taker. Any volunteers? Volunteers.
I'll try.
Excellent. We have a volunteer for note taker. Thank you. Let's see. So first up today, am I using this thing wrong? It seems to be a little bit off. So yesterday we had the tutorial. I think probably most of you who are here were in the tutorial. If not, you want to watch it. It's available up on the on YouTube already. Quality seems to be very nice in terms of audio and video. So today, here's meeting 2. We're going to cover some IDs and some stuff. Just to reiterate, in case there are people either in the room or online who are not, this group was started in January of 2018, or kicked off as an idea anyway. And by November, we were at the status of proposed RG. The tentative plan is to continue meeting at IETF at least once a year, but to also have meetings at quantum computing or quantum networking conferences, and hopefully also online. So we don't yet have a plan for a specific date for the next meeting, but likely it will be in the fall, possibly at a conference, or possibly in Singapore. So we'll discuss that on the mailing list. So the agenda for today, let's see. So that's where we are. Drafts we're going to talk about. There are several drafts already up. Everything is in data tracker at this point. There are 4 we're going to cover, and then a 5th short report on what happened at the hackathon on Saturday and Sunday. So let's see. First up, Wojtek. You want to come up? Let me pull up your slides here. And while I'm doing that, while I'm pulling this up, remember everyone, please sign in the blue sheets. Please sign the blue sheets. Let's see, PDF. And also, as a reminder, when you do come up and ask questions, please give your name. And please, I know everybody's used to saying their own name, but please to say it slowly and clearly so the note taker can pick it up. That would be a big help. Wojtek, you want this?
Yeah.
Use the left, right arrows, not the other things. Hang on, let me put this in full screen mode. All right, there you go.
Okay, hi everybody. I'm Wojtek. I'm a postdoc researcher at QTech at TU Delft, which is part of the Quantum Internet Alliance. What I'm here to present is essentially what I want to actually pitch an idea of, say, work we could do as a research group together. The draft up online is more only like my idea and proposal of what it could look like, rather than an actual proposal of a document that should go forward in its current form. So what do I want to propose? What I would like to propose is that as a research group, we work and devise a set of goals and principles for a quantum internet. as a group that actually combines expertise from both physicists and experts from classical networking. Because as Rod has pointed out yesterday in his tutorial, there's a lot that physicists don't know that they don't know, and that we need help from people who actually understand layers and network architectures, from people who have been building these networks for 20 or so years. So first, quantum networks are imminent. First lab demonstrations are going to be happening in a few months. And the first connections between several cities in the Netherlands will happen next year. The plan is to connect Amsterdam, Hague, Leiden, and Delft in 2020. There's no quantum network stack. They're basically connected at the very lowest level. They have basic connectivity point to point, but there's no, there are various ideas floating around of how to connect them in a coherent network. How should we go about defining them is a different question. There are proposals from Japan, Innsbruck, Delft. So yeah, different groups working different architectures. Kind of the
Let's see
off. Yeah.
Am I doing something wrong with the Chromebook here? It's not. It's not
maybe
paging at full
just
pages.
press F11
F11.
for full screen.
There's no F11.
Would you at least be able to scroll up so I can show the whole slide?
You want to show me what I've got wrong here on the Chromebook?
No, just the one above. No, the.
It's what I needed to hit the.
Okay. Yeah, that works.
And your clicker should now go correctly?
Okay, thank you very much.
So I needed to push that little plus icon first?
Yeah, so it's full screen
And then the other.
and then the other.
Okay, continuing. So where am I coming from with this idea? Essentially, so the classical internet, when it was built, it had a set of goals guiding what trade-offs should be made and what is the fundamental goal that it should achieve. For the classical internet, it was essentially, I'm going to read out from a paper by David Clark. The top-level goal for the DARPA internet architecture was to develop an effective technique for multiplexed utilization of existing interconnected networks. The goal of the classical internet was you had ARPA and you had a bunch of other networks which you wanted to connect to, and they wanted to connect all of them. And they had a bunch of secondary goals which they defined as like, what other goals do they want to achieve with the architecture for their internet protocol, for the TCP/IP stack? And they are in the order of priority as they defined them. And they primarily wanted the internet communication to survive despite losses. They wanted to provide different types of services. They wanted to accommodate a variety of networks. They wanted to permit distributed management of resources, cost effectiveness, the ability to connect with a low level of effort, and that resources must be accountable. And if you read David Clark's paper, The Design Philosophy of the DARPA Internet Protocols, essentially he summarizes that the first few goals were achieved spot on, but the last few goals were kind of sidelined and only partially achieved. And there's also an RFC, 1958 to be specific, which outlines a set of principles for the classical internet. So this is just a summary of where I'm coming from and what there is for the classical internet in terms of goals and principles. And the question is, what are our goals? So I submitted a draft which is more like an idea, a proposal of what a document that achieves this could look like, in which we suggest basically, there's a suggestion that perhaps our priorities should be more about, because we don't have a goal, the same goals as the classical internet, we don't have an ARPA network to connect with an ARPA radio network. Should probably more focus on supporting distributed quantum applications, focusing more on heterogeneity, being flexible with regards to hardware requirements, because quantum hardware is incredibly difficult, and some security. And the thing is, there's question marks in number 7, because I'm almost sure that like there's things missing. Some of these might not have to be here. Why I think we need that is essentially like the trade-offs must be made. It's difficult to achieve a good for everything architecture. Question is like, what should we prioritize when we're building a quantum internet for the purposes of users and applications and network operators, and essentially serve as a guide for all the people who are designing the network. And a question to the QIRG community here is essentially like, would people in the community find it useful for us to define such goals? Would it be useful to work together to define these principles? and is the QRG the right place for it? And as an output, I'd see essentially a document published by the QIRG, outlining these goals and principles and outlining the thought process by which we reached them, and possibly also an academic publication, because there's still a lot of academics working on this. Who should be involved? I think, so specifically there's a lot of physicists who are interested in this, but I think I explicitly want to ask the networking people who have expertise in classical networking. It doesn't matter that you don't have any quantum physics knowledge. It'd be very good to see your contributions and ability to discuss and talk with physicists about about your experience about building networks and network architecture. So yeah, I stand and I leave these questions to the community.
Is that it for the slides?
Yeah, that's it for the slides.
All right. Questions, comments, complaints, criticisms? Yes? Okay, Robin's having trouble with the connection to the Jabber chat room. Is anybody on the Jabber room at the moment? Nobody in the whole room is on Jabber? That seems unlikely.
Some of the questions that from the room that could also be asked is like, if you think something else should be done, perhaps a different way to collaborate to draw in classical networking expertise, that's also could be a suggestion.
Hi, Tim Jones. I'm involved in a project that's building networks that connect European national research networks together, and we're interested as part of that project in potentially exploring quantum key distribution. So I think the question would be, in building that network, what are the considerations for putting this in place perhaps alongside it? Do you need separate dark fibers? Can you use existing wavelengths in some way? So those sort of considerations for people that are building existing networks as to how this may or may not sit alongside it would be very useful.
Thank you. That's a good point. Completely missing from the current draft is like, yeah, what could be a practical way of merging it with existing telecoms, and how to actually make it a practical technology? Thank you.
Other comments, questions? Let me ask as chair then, how many people have actually looked at the draft? Oh, we got a dozen or so. How many of you think that this is something that you would like to see pushed forward? Excellent, twice as many hands. How many of you are willing to put in work to make the document happen? That looks like a pretty good number. So as RG chair, let's see, so I think we would, so you're asking to push this forward from an individual draft to an actual RG work item?
Yeah, so this should be addressing the first, to me, it addresses the first point of the work items on the agenda. And what I would suggest is, yes, to collaboratively work on this draft and actually produce a newer, fuller version. That's part of the QIRG.
Is there a consensus in the room then that we should move this forward as an actual RG document? This could be the actual first work product of the document. People who think that's a good idea. That's pretty good. I want to actually confirm that on the mailing list, but I think we have, unless there are objections raised on the working list, I think we can take it forward as an RG working item.
I think the next step should be on the mailing, will be taken on the mailing list. Okay.
Good. Thanks. Let's see. So next item on the agenda, Axel, you want to come? Let me pull up your slides here. Clicker's right there. Perfect page. There we go.
Perfect. Hi, can you hear me? So I will talk about a draft that's on the service of a link layer in a quantum internet, which is by myself, Matthew and Stephanie at QTech in TU Delft, where we're also part of the Quantum Internet Alliance. My goal today is to just give a brief presentation of what's in the draft. I will not go into too much details because I would like to more have feedback from you of if there's questions or comments or what to improve. So maybe just before I start, who has had maybe a brief look at the draft of the audience? Could I see a raise of hands? Maybe? Okay, one or two. Yeah.
And one behind you.
Perfect. And myself. So the scope of the draft is to try to define the service and the interface of a link layer from higher layers in a quantum network. But it doesn't concern a protocol that realizes this service. But I would just like to point out that we recently put a paper online that does propose a protocol that satisfies this service. And you can find it on this link. It will also be up in the end of the presentation. In this paper, we also fully implemented this protocol in a discrete event simulator, and we've done some quite extensive simulations. But that's a separate thing. You can look at this paper if you're interested. But the draft I'm talking about today is more to try to define the service and interface of a link layer. And just to get started, as you're all aware of, in the most simple way, the link layer of a classical network, the purpose is to send a message from, or maybe officially a datagram, from one node to another, which are connected through a link, possibly with switches in between. And your first thought might be that, similarly in a quantum network, you would send a qubit from two nodes which are connected through a link. But what was also explained very well by Rodney and Tracy yesterday in the tutorial, if you haven't seen it, you can also see it on YouTube. I think it's uploaded already. The most fundamental building block in a quantum network is not to send a qubit, but rather to create entanglements between nodes which are connected through a physical link, possibly with repeaters in between. And why this is the more fundamental building block is that you can then use this sort of short distance entanglement to make longer distance entanglement with the operation called entanglement swap, which you can also was explained yesterday in the tutorial. And such entanglement can also be used to teleport a qubit. So if we have this short distance entanglement, we can create long distance entanglement and then have a long distance qubit transmission. So in this paper I mentioned, we also propose a functional allocation of a network stack for a quantum network, where the link layer is above the physical layer. And its task is to produce entanglement between nodes which are neighboring nodes in the network. I won't go into all the details of the draft right now, but for those of you who had a look at it, just a short sort of recap. The idea is that a higher layer essentially sends a message, which is to create entanglement or request to create entanglement of one or more entangled pairs. And together with this message, one can also specify a desired minimum fidelity. Again, this was explained yesterday in the tutorial, what it means with fidelity. Together with a maximum waiting time that the application or the higher layer is willing to wait for this entanglement to be generated. And the reason for this is that there's usually a trade-off between how high fidelity you can have and how fast you can go. So usually if you want higher fidelity, you have to wait longer. And the higher layers can then give an idea to the link layer of how long it's willing to wait and what minimum fidelity it needs. There's also a specification of the actual message in the header format, and it also contains, for example, a priority or a purpose ID, and also things like one can specify whether one wants to measure the entangled pair directly when it's generated, for example, for producing key. The reason for this is that in some cases you can actually go faster or generate entanglement faster if you measure it directly. And if you want to know more about this, you can also ask. But for the remaining time, I would like to maybe have some more discussion with some specific questions. So one question is from above, is this service that we define in this paper what an application or a higher layer actually wants or requires? Is there something that's missing or something that's redundant in the draft? But also from below, is this, from a hardware point of view, feasible to implement? In Delft, we have a hardware which is built on nitrogen vacancies in diamonds. So we come sort of from this point of view, but it would also be very interesting to see groups with other hardware, whether what we defined here makes sense for them and what limitations there could be. Maybe some hardwares can only do subsets of the commands that we specify, and what such subsets could there be. But also the continued work on the draft. So this is the first time I write a draft on defining an interface of a link layer. So for me, it would be very helpful for if someone would like to that has done this before to contribute and maybe say what's missing, what should be clarified, to go forward with the draft. I should also say that I actually misnamed the draft when I uploaded it, so it doesn't say QIRG, so it's a bit hard to find, but I think we can solve
I
that.
got it added into the group documents on the data tracker. So if you look at the QIRG page in data tracker, it's now listed there. We'll get the name straightened out probably at the next upload rather than fixing it, rather than changing what's already there.
Yeah, excellent. So maybe I would like to make room for some questions or feedback or discussions, and I will leave up the links to the paper and the draft while we talk.
My name is Hirotaka Nakajima. Thank you so much for this presentation. Could you show me the header of the header format page? I'm wondering you mentioned about the node ID, but could you explain what do you expect for the node ID?
Yeah, so there could be not only two nodes, but multiple nodes. In some cases, entanglement generation is done by a midpoint. So the node sends photons to a midpoint, but it could be a single midpoint for more than two nodes. And then if you want to generate entanglement with a node, you want to specify which node. For example, sort of like an IP address.
Okay, so so I thought that it could be like a MAC address for the classical network, but you mentioned about like it's kind of IP address. So in this case, like you mentioned, at this moment you mentioned about like node ID, it's a 32 bits, but it could be more if I'm sure. But in future, there is a lot of quantum computers deployed on this planet, so it could be we should consider a little bit more wider space for that. Thank you.
Yeah, thanks. That's a good point, and that's maybe a good questions to further discuss on the email list. How should we specify nodes in a quantum network? So addressing. Yeah.
So is your question on the same topic, or are you moving to a different topic?
It's exactly
Okay,
the same.
go ahead.
Hey, Tobias from LMU. You want to send it over a classical network, right? Or is that a quantum package?
You mean the create
This,
message?
yeah.
Yeah, that's classical. That's
So
fully classical.
why not just use IP?
That's an option. Yes.
Okay.
Yeah. But I guess it's good to discuss and see.
I think the question is does node ID have to be different than how we use node IDs in today's internet? Do you have a requirement that it be different?
Not that I can see. I think it's the same. Yeah.
So I had a question. I'd already prepared a question on this exact topic. So not as chair, but as a personal questioner here. This is I had seen the same thing. I think, as I understand it, this remote node ID is a specifier for a neighbor. Is that's right? This is not a network-wide identifier.
No. Yeah.
Correct?
Yeah.
Okay. So this is, It only has to, the number space has to be big enough to identify everybody who could possibly be an immediate neighbor for the creation of physical entanglement. Is that right?
There is to respond to this. So there is a node ID in the response, which we plan to use to essentially identify the entanglement. And the idea is that this entanglement ID should be unique in the network also. And it's built from the ID of the node. So in that sense, it actually also needs to be unique in the network.
Okay, so these need to be network unique. Okay.
So
Your name again, please.
This is Dino.
Yeah.
This needs to be sent over a classical point-to-point or multi-point network, or is it using some other path?
So this message is sent locally, essentially at the node from
Over what physical interface? Over the air?
classical,
Classical.
just locally.
And is it usually on the other side of this, say, Ethernet? Yeah, it could be, right?
Mhm, yeah.
Okay. And if these are defined to be point-to-point, then you don't need a node ID because it's always the thing on the other side. Do you expect that the receiving node look at this packet and say, remote node ID field equals my node ID, therefore I should use it? Otherwise, what do? Do you forward it? Do you drop it on the floor? Did the sender was an error? These are the sorts of things. So if it's defined as a point-to-point network, like we've done with other protocols, you can just use link local addresses. You can use multicast addresses at the link layer just to get things hop by hop.
Mm-hmm. Yeah, so just to be clear that this message, this create message, which is this header format, is not sent to another node. It's sent locally to the link layer protocol, which is then generates the entanglement between the nodes.
So this is an interlayer message then.
Yeah.
This is not a message that appears on the wire.
No,
It's not a protocol. Okay, that clears up everything. So
Maybe I'm
But still, it has to
misleading.
name nodes that name other nodes in the network.
Yeah. Yeah.
Okay.
So it could do that with a socket interface by using IP addresses, right? It doesn't need to be encoded in the API payload, right? I think I'm answering my own question. I don't think it does.
Okay,
Yeah.
okay, that's good.
Dave Wheeler. One of the things that I'm struggling with, and it may just be my naivete, is what's the topology relationship between the classical network and the quantum network? And that would help me understand what you're trying to do with the remote node ID. So, obviously that may change from different implementations, but that might be something that would help those of us new to this field to understand what's going on and how those relate back and forth.
Yeah. So that's actually, I think, an open question of what would the topology actually be, and maybe that's an interesting work question to work at. The topology of the network.
Yeah, because I can't understand what a remote node ID would be, at least in my brain, until I see some type of topology and how we're working to move these messages around. It just doesn't make sense to me yet.
Yeah, Tim Chan, I'd just like to echo that comment, and it kind of goes back to my earlier comment. The other thing, if I understood yesterday's tutorial correctly, was that in order to move quantum state from one place to another, you need to send a couple of real data bits. So again, understanding how that fits in with this would be useful as well.
Yeah. So I would say that the teleportation is not part of the link layer. Here, the link layer is responsible for generating the entanglement. And yeah.
Okay, I'm Maran van Hees from TNO, also affiliated with QTech somehow. I'm very interested in the capacity of this network, because if you look from an application side of things, you can request, I want high fidelity, high capacity quickly for my application. That's not possible yet in current state of the hardware. So how can you deal with that in this type of protocols?
Yeah, so there can certainly be messages coming back which says this is unsupported.
Mm-hmm.
For example, if you request a very high fidelity in a very short time, the hardware might not be able to respond to this. And then it can say unsupported. And then it's up to you to decide, do you want to continue? Yeah.
So that should be woven into the application itself at this point. And how does this link with the priorities if there are multiple requests at once in the network?
Yeah, so that's a good question. We have done some initial work on sort of investigating scheduling strategies, which is part of the paper I mentioned. But I would say that that's still a big open question, actually, how to do scheduling based on a priority and the different requests. Yeah.
Okay, thank you.
Hello, Grigory Marshalka, Russia. In order to provide authenticity of the remote node, so in order to withstand the man-in-the-middle attacks, the remote node should be authenticated. That means if you incorporate your protocol in the IP, then this remote node ID could be irrelevant because the node will be authenticated at IP level. So we should think. I think you should think about it whether this remote node ID should be here or maybe at the higher level layers.
Yeah, that's a good point. Okay.
Hey, Tobias again. It looks a little bit similar that you could, so if it's not an IP address, if it's a local link, it could be something like ARP, so mapping between an IP address and an actual node with a MAC address kind of thing, which is your remote node ID. Is that something which could be an idea to just define like a layer between IP and quantum MAC?
So I should say that the task of the remote ID or the purpose of the remote ID in the create message is basically to if you have different physical interfaces to, for example, a midpoint where you can create entanglement, you just need to specify which other physical remote node. But in the response, in the OK that entanglement has been generated, it has a different purpose actually. So there it is used to identify the generated entanglement based on the IDs of the nodes that hold the generated entanglement. So I just wanted to say that here I put them as the same thing in the create and the OK, but in the create it actually has a different purpose than in the OK. So they could be different in principle.
So there could be multiple entanglements on the same link?
Yeah.
Yeah.
If you have memory, you can store multiple qubits. You can have multiple generated entanglements.
Okay, thanks.
Yeah.
Hi, this is Dino. Let me just ask a really simple question. If I want to do entangle and I'm one side of the pair at my house and the other pair is in your lab, will I send this message from those two endpoints across those capital I internet?
You mean the create message?
Yes.
So the create message is locally at one node.
Okay.
Yeah.
And then what happens from there?
So that's part of the protocol. So
Do I send anything over the network to talk to your lab?
yeah, in our proposed protocol in the paper, we do that. Yes.
And that's not this message format?
No.
Okay. And in the paper, you specify it?
Yeah.
Okay.
All right, let's make this last question.
Giovanni Saidian. Is it a goal like to reuse much stuff as possible on the classical internet, and anything new you create, they have to justify why you're choosing that particular parameter, like for example, remote ID. It's something that you envision like we can only create new stuff if it doesn't work, and because we have those requirements.
Yeah, so I would say that we should maybe only invent new stuff if we actually need it.
Yeah.
And for addressing nodes in a network, I don't think we need to reinvent how to do that. Yeah.
All right.
And as both chair and an individual, I would say absolutely yes, we want to avoid reinventing things. We want to use everything we've got possibly. All right, let's see. So This is currently at the status of an individual submission. I was not planning on taking this one yet forward as an actual RG working item. I think we can keep this as an individual draft for at least another draft or two.
Yeah.
Is that true? Okay. So let's do that. Let's keep this as an individual draft, but this discussion, all of these questions were really outstanding, and every single one of these needs to be answered in the draft as we go forward. So I'm certain our note taker did an excellent job there, but if anything doesn't show up in the draft eventually, it'll get please bring it back up on the mailing list as we go. Anything else? Good.
Thanks.
Thanks. All right, next draft up is actually mine. Let's see. Connection set up in a, whoops, hang on. Hit the wrong place. There we go. Page full screen. There we go. All right, let me step down here and do this from down here. Since I'm sharing this alone today, I'll have to kind of keep track of the clock. But if anybody wants to keep track of the clock for me as well, that'd be good. So we put up a draft on connection setup in a quantum network. We're doing a bunch of simulation work at the moment, but we're trying to make it as hardcore realistic as we can in terms of all of the work you have to do to bootstrap the entire network, and as well as actually getting the connections going on. So this is a framework document for how we are currently establishing connections inside our simulator. How many people have actually looked at the draft? This one was posted right around the deadline, so probably only a handful. Okay, so comments always welcome. So the idea is you want to create a connection across multiple hops from place to place. The middle nodes, as we've said, have to perform the entanglement swapping and the error management. So Bill Monroe wants to connect from there to the quantum internet, distributed data, IT, computing house, or Quidditch. And this means that we're going to have to find a path through this. We are not talking in this document about the actual routing process. That's separate, but we're talking about the set of messages that have to pass from place to place in order to make all of this work. So this is planning the sequence of operations and then convey that sequence to the nodes, constraints and assumptions. One of the things, again, where the physicists sort of fail to realize what happens in even a medium scale network, let alone something like the internet, is that there are a great number of characteristics of the links and nodes that are on the entire network that are a priori unknown to you when you're starting to try to create a connection. So part of what we're trying to do here is figure out how you're going to collect that information that allows you to decide how a connection should operate. So each node has a certain amount of information. It knows its own capabilities, including the number of qubits that it has, the amount of memory, and the lifetime of those, and the fidelities of the operations it's going on. We're assuming at this level that it knows who its neighbors are, and that includes knowing things about the link itself, including how many trials per second you're going to be able to do for building entanglement, and what the probability of success of those is, and what the fidelity is. And we're assuming that it has at least some local knowledge about the topology with some routing metric available, and the gateway from the local network to the outside world. Although at the moment this draft only covers single network path creation. It doesn't yet cover inter-AS or the equivalent of that. Information that each node does not have is it does not know about what every node on the network's entire hardware capabilities are. It doesn't know what the fidelity of the entanglement is that will be created, and about the amount of memory in every node, and doesn't know about the local operations. And certainly when we go from single network to inter-networking, as with ASs today, the amount of information that's going to be allowed outside of the perimeter of a particular network about the internals of that network, we're trying to minimize that. So if you want to cover a series of networks, and Bill's house is up here on the left and the Quidditch server is up there on the right, you got to find some way to make a path between the two, and all of the other is opaque to Bill, or at least not known until he tries to connect to that. I'm not going to cover that inter-networking stuff today, only the individual network connection. So Bill knows that the gateway to the outside world is there, and an undefined metric for the routing picks this path as we go.
I'm
Yes.
already confused because I don't know which network you're talking about.
Which network?
Are you talking about these are links between routers and an IP network, or these are links between entanglement repeaters?
These are links between entanglement-capable repeaters. Thank you. Thank you for the clarification. Sorry. One of the things that we didn't say when in the Q&A with Axel is at the level of creating this entanglement, there's always really hard, super hard real-time stuff that has to go with this that's not specified in this, really low-level physical layer signals. And those will have to be carried in the same channel as the actual optical signals that are creating the entanglement. But then there are sort of soft real-time messages that get exchanged for, hey, did that work? And what are we going to do next? Right? So those could be carried over a separate IP-like infrastructure, and that does not necessarily have to have the same topology, but of course you have to be able to identify who those other nodes are. So only the really low-level signals have to go in the same channel, but of course you have to be able to talk to the other quantum nodes via some classical mechanism. And at the level of the socket, that doesn't matter whether the topology is the same or not, as long as you can name who that node is.
So between the entanglement repeaters, there could be an IP network.
Yes.
Okay. Will there always be, at least for starters?
If we succeed in defining all of this as running over IP, then yes. The alternative would be, somebody tries to create an entirely separate classical network for doing this. We can do it over, I don't know, SS7 or ATM, or take your pick, right? No, let's do it over IP, right? So yes, these are all quantum links on this. Bill knows this is the set of quantum links we have to cover to get from here to there. So how do we get the information about all of those links to be able to build a high quality network or a high quality connection from here to there? Bill starts with a particular request. He sends that request to his neighbor, and he starts by putting in the information about the SA, the link between the nodes S and A, and about the information about the connection he wants to create, and who he wants to send it to. He sends that to node A, that then adds information about its next neighbor, about that next hop A to B, sends it on to B. B adds some additional information about the BC link, and you keep repeating. And as you go, you are accumulating information about the set of links between yourself and the gateway. And then eventually you get to the gateway. Then the gateway's job, node I in this figure, is to take that information and plan this connection. Those entanglement swapping operations and the purification operations we talked about yesterday. How often are we going to do those things? How many rounds of purification? How long are you willing to wait for all these things? Everything you have to do in order to build a connection across multiple hops. I is going to decide what everybody's responsibility is for this particular connection. So, question? Yes.
Clarify question. Giovanni, SIDN. So this is like a virtual circuit that you're trying to establish?
Yeah, pretty much, right? Yeah, this is actually, that's a good point. I didn't say that, and I meant to say that at the beginning. Because as I discussed yesterday in the tutorial, at this level, these first generation networks, building this entanglement end to end is a distributed computation. This is not stored and forward stuff. All of these nodes, S, A, B, C, D, E, F, G, H, I, all of these nodes are going to be involved in building this entanglement. And so they're all going to be cooperating. There is going to have to be state at those nodes. Right? Some of the earlier work we did, we sort of fudged at the edges in some simulation work that we did earlier, and we did it without what you would consider really to be connection level state in this. But the reality, as we get more and more detailed in the design, we're finding that it's really going to require state for those connections at the nodes. Yes.
Hi, this is Albert. I'm still confused. Between A and B, there is a quantum link, right?
Yes.
But then I'm assuming that there is also a classical link, right?
Yes.
That's how. Okay, so this is a network, a quantum network topology, which overlaps a classical network topology.
Well, the diagram represents the quantum topology, and we're assuming that S has a way to get classical messages to A or B or C or anybody else in this network. But the way it's getting them to this is we are forwarding this hop by hop through this network. There is no requirement that classical communication infrastructure have the same topology, but you have to be able to reach all of the nodes that you might need to communicate with this. So the topology for the IP network could be entirely different. If we were doing this in a room this size, they might be communicating via wireless LAN, right? It doesn't matter.
Well, to some extent, yes, right? Because you are forwarding the message through the classical, you are using the topology to discover the path towards the final node, right? And you're following per link. So to some extent, there is an overlap, right? Or maybe I'm confused.
The natural thing is for the topologies to match up, but it's not a requirement. Okay. There might be multiple hops between S and A on the classical network, but there are not in the quantum network.
Okay, thank you.
Let's see. So we're running a little short on time. Let's make this the last question.
Tim Chanson again. So these are classical messages that are passing.
These
around.
are classical
This is more
messages,
like
yes.
sort of RSVP type of.
Yes.
Messaging
So
with
RSVP.
state.
My office used to be 2 doors down from Bob Braden. So yes, RSVP like. Right?
And is there therefore a path message coming back afterwards?
That's the other half of the presentation is
okay,
A builds this sort of stuff, or sorry, I builds what the set of rules describing what each node in the network should do, and it sends them back, and they sort of go hop by hop, and each node takes its share of that connection information off of it and sends it on back. In theory, it could also be unicast. I in that figure, in the upper right there, could also actually send each of those messages separately to S, A, B, C, D, E, F, G, but we just assumed it's a stack and that they pop stuff off the stack as it goes back. Could also be alternatively the other way. And that's pretty much it. There were a couple of questions already on the mailing list. Somebody asked, is this similar to segment routing? And I know some of the older literature on things like waypoint routing and a little bit about things like that. Those are the kinds of things I had in mind, but I'm not very familiar with segment routing. If segment routing can do this, can carry this kind of information, I'd be entirely happy to build this over top of segment routing. We have not defined packet formats or anything like that. We have a good idea of what the information is that needs to be carried, but we have not picked how to carry it.
Tim Chan, so your segment routing would allow you to specify the path that you follow through the network. So it wasn't clear to me how you knew you were going along that path from A to I. Just assume that's normal routing.
It is. It's going to require a separate routing table. It's not going to be the same as the classical routing table, but it can be identical in terms of technology.
But if you wanted to pick a different path, different to the standard path the packet would take following the routing tables, then you could use segment routing.
Yes. Is yours quick?
Yes. Max Franke. What would happen if the quantum node fails in your method? Like the quantum node would fail on the quantum level, so it would have no way to tell on the classical level, like the receiver or the sender, that it failed.
Well, we assume there's classical hardware monitoring all of this, and so that sooner or later, all of the monitoring stuff will figure out, that one of the nodes in this path actually failed. It could be, maybe D fails in the middle of this. What to do about that and how to route around failure, we haven't gotten that far in design stuff yet.
Okay, thank you.
All right. That's it. Thanks. Let's see. All right, time-wise, we're running right about on time here. Shota, you want to come up for your presentation? Let me pull up your slides. On the agenda, I actually listed the there are not slides, but you will find in the drafts at the bottom of the page, you will find that the draft calls QIRG advent, which should probably have been advert, or no, I guess that's abbreviation for advertising entanglement in it. I get it. Advertising quantum entanglement networks and capabilities. This was submitted as an ID and discussed in Bangkok, but at the moment seems to be sort of quiescent. Anybody have any comments or anything on that? If not, we'll take that up on the mailing list for whether or not we want to take that draft forward. I don't think any of the authors of it are actually here. So all right. So we'll bring that up on the network then, or on the mailing list. All right. So let's see. Last presenter here. Shota, you're up.
Okay, Shota Nagayama is speaking. So I will talk about a brief summary of the hackathon and my project Quantum Ping. So in the IETF hackathon this time, so we had one group of quantum networking, and we had 3 projects, and one of that is implementing a routing on the simulator called Simulacron, the Axel implemented. And my project is this Quantum Ping. So I will talk about this. And the last one is about blockchain integration in quantum networks. So the Quantum Ping group did in this hackathon. So first we define the Quantum Ping, and writing draft, the internet draft now. It will be to appear in next IETF. So the quantum network consists of actually 2 types of planes. So the first is quantum plane, of course. So here, of course we want to send a photon and want to create entangled pairs. And in classical internet, we want to in this plane, so we need classical information and management to control quantum plane. So this is for that purpose. So first we thought about what is the reachability in classical internet. So the reachability refers. This is from Wikipedia maybe. So the reachability refers to the ability that a pair of nodes at least once succeed to communicate datagram in both directions from one node to another node. And this succeed or confirms, so the node on the entire path can forward received datagram to the next. And of course, those nodes have a good routing table to achieve that. So in quantum version, those correspond to those. So the purpose is actually to generate a better pairs between 2 end nodes. And this success to generate better pairs confirms that the nodes on the entire path between the 2 paths have a ability to execute entanglement swapping for routing. Of course, that entanglement swapping works proper, and the routing has to be proper. And actually, in classical network, errors are implicitly managed well. So in layer 2, the CRC code works, and in layer 3, the IP headers are checked by checksum. So, and in quantum network, we have to take care of fidelity of pair pairs. So fidelity is a kind of measure of errors in quantum information theory. So the problem in quantum network is that the generating cost of pair pairs are so expensive. So actually, we don't want to waste the consume pair pairs for the quantum ping. So because we want to reserve pair pairs for actual applications. So this is like this. So we have a quantum network, and okay, let's do ping. So there could be a so end-to-end pair generation is so expensive and there could be a bottleneck. And we don't want to fulfill the network with just quantum ping. Then what we thought was, okay, let's share statistics of such bottleneck link between multiple different quantum pings. So let's think about this 1 and 2. The first one is entanglement swapping for routing and entanglement purification for managing errors. So let's divide the health check statistics to 2 parts. So the first one, and the first one is here for routing, and the second one is routing in a node, and the second one is link between 2 nodes. So the checking the status of a path can be consist of those 2 types of statistics. And so actually, so this can be the health check of this part can be done in a local node. So it's very easy compared to the different nodes, between different nodes. And actually, so for this link, so when we so this link of course can be busy, but when it is available, so we can make statistics to check the state tomography for this link, the Bell pair created in this link. And actually, so in the entanglement purification, the success, even if this link is busy, the success rate of entanglement purification depends on the low fidelity. So we can estimate the fidelity of a busy link. So collecting, okay.
Hi, Giovanni, SIDN. Clarifying question.
Yes.
Traditional ping is an active measurement approach. And am I getting this
Hang on,
right?
sorry, let me interrupt you for just a second. I see a couple of people are starting to filter out for lunch already. Anyone who has not signed the blue sheet, please do so before you leave. Blue sheets are still circulating around. Okay, yeah, sorry.
Yeah, so traditional ping is an active measurement approach. And is this like, am I getting this right? Is this like passive measurements? You just observe what's in there? You don't generate anything?
Yeah, kind of, but these statistics can be updated very quickly. So
with active probing or passive monitoring?
A kind of passive monitoring.
So quantum ping is passive, all right?
Wait, 2 minutes. 2 minutes, Jota.
So actually, so everything is done in the classical network. So we don't do the we don't send a new quantum message for this quantum ping, but that works as a quantum ping. So that confirms what we want for quantum ping. Yeah, basically that's the end of my presentation.
That's it? Okay, any last questions? If not, that's everything that was on the agenda item, everything that was on the agenda for the meeting. Any comments or questions or any other business before we adjourn?
Kiran from Huawei. Yeah, a question for you. Is this something we can try out? Is this a simulator platform that we can try out ourselves? It's available for us to use?
So now it's not available. So.
No, just Giovanni said, and just another comment. I think this is great work because it's going to make quantum networks more concrete to operators like me. So
thank you.
Great. Anything else? Good. Thanks, Shota.
Thank you so much.
Any other business? Anything else? If not, we will adjourn and we will see you on the mailing list, and we'll schedule the next QIRG via the meeting via the mailing list. See you online. Blue sheets, please return to the front. And anyone who doesn't, who hasn't signed it, please do so. Yes. Yeah, it's all right. Yeah, I hope nobody on Jabber needed us. Yeah. But apparently nobody else in the room was on there. This keyboard is terrible. It causes all kinds of typing problems. How are you? Very well.